Okay. Okay, so before start, I will introduce myself that I'm Richik Datta and currently I'm pursuing MTech in second semester from Department of Energy Science and Engineering at IIT Delhi. And before pursuing MTech, I have completed masters in physics, so I've written my GATE paper in physics. So these things are pretty similar for me. And those you are, I don't know how many of you are preparing for GATE, NET, or others. So this will be beneficial for you. So we are going to start about the nuclear models. So before getting into this part in nuclear model, we have to know about what is nucleus, because it's very preliminary stage. Second. मृदांशु ये स्लाइड्स मूव क्यों नहीं हो रहा है? मे बी फॉर द एनोटेशंस.
Sir, you can try slideshow.
Slide show. Oh yes, but the thing is not working here. Stop. Hmm, stopping and let me start again. Yes, the contents are not. Is this visible for everyone?
Yes, it is visible, I think.
Hmm. Okay, so before getting into the nuclear model part, we have to know about this the what is nucleus. So everyone know, because this is very elementary. I think class 10 level part, that the nucleus is the core of an atom made up of protons and neutrons. We all know that proton is positively charged and neutron is very pretty much neutral. And cloud of and they are surrounded by the cloud of negatively charged electrons. So nucleus is positive and the revolving electrons are negative, so that both positive negative charges make the atom in a very neutral state. Other there are many excitation energy, and these things will happen. That is the another issue. So before enter into this nucleus, we have to know that the quantum mechanical approach. I don't know how much of you are pretty sure about this, the quantum mechanics and atomic physics. So do you know about the basics of quantum mechanics and atomic physics? Everyone, those who have joined.
Yes, sir.
Okay. So today we will discuss a little bit things about these the quantum mechanics and atomic physics, because if you don't know about the elementary, so you will not get about this the nuclear models. So there are various nuclear models. So so let's see the generic symbol of this the nuclear model is there is the ZXA. The ZXA that, but yeah, that is the X is defined the symbol of the element. If you all know that the carbon, you will see that the for the carbon atom, if you see that we can write this the nuclear models that for the carbon atom we can write for any isotope, isobar, isotone. Do you all know about this the isobar, isotone, and isotopes? So I'm not discussing. So the generic symbol of the nucleus is the XZ. So Z is the atomic number. Atomic number means the total number of protons present in the nucleus, and A is the mass number, total number of proton and neutrons. So mass number is total number of protons and neutrons. So this is very basic thing that if I will give you the some random atoms, so X something you can take the oxygen O 16 8 isotope, oxygen of isotope O 16 8. So what is the number of protons and what is the number of neutrons, you can easily determine that from this the generic symbol of nuclei. So what is the number of protons of oxygen 1608? Can anyone say? Can anyone guess that what is the number of oxygen, how many number of protons in the are present in the isotope of oxygen 1608 isotope? Okay, so this will be the number of protons that I have already told that A is the mass number. So total number of protons and total number of neutrons are present there. Uh, is and Z is the atomic number of protons. So if I am telling about this the atomic number of protons, total number of protons are 8 from the 1608. There Z is 8. So you can easily get the atomic number is 16. So A equal to Z plus N. So from that the neutron number will be A minus Z. So that will be equal to 16 minus 8 equal to 8. So the total number of proton is 8 and total number of neutron is 8. Okay. These are the very basic things. I am not wasting any time in the particular things. So let us go forward. So here you can see that the various size of in what's inside in our inside in the atom. So that you can see that the atoms are present in a particular system is 10 to the power minus 8 centimeter. The size of the atom is 10 to the power minus 8 centimeter. So and the you can see the size of the electron is near about to 10 to the power minus 16 centimeter. And so there are atoms are present in the, so if we go there will be the proton, neutron, electrons are present. And again if we go further there will be arouse a very particle part of the particle physics will arise, where before maybe up to 19th century there are many scientists who were there who were used to believe that there are inside atom only proton, neutron, electrons exist. But later on after 20th century where technology gets advanced and scientists have done more research on it, they have seen that there are so many uh, tiny particles which are smaller than proton, neutron, even electron are present in the atoms. So these are another branch of the physics has opened. This is known as the particle physics. So there are many subparticles are there like meson, uh, boson, fermions, neutrino, antineutrino, baryon family has occurred, mesons family has occurred, and then after that, nowadays a researcher going into the quarks. So if we go beyond of these particles that I mentioned, that proton, neutron, electron, meson, meson, baryon, if we go further, there are more smaller. This is known as they are known as a quark, and another part of the quark. If we take this quark, then will we get these strings. The strings are the smallest object in the universe till now. After Big Bang, the smallest object in the universe till now is the strings. So these are the basic elementary idea regarding this. So atom has the size of near about 10 to the minus 8 centimeter. So anybody can guess that 1 angstrom means how much meter? Can anybody say? I am asking very basic questions. Does anybody know that 1 angstrom means how many meter? How much
10 to
meter?
the power minus 10.
Yes, the 10 to the minus 10 is correct. So let's move forward. Okay, so this is the main thing of the basic properties of nucleus. So this is the binding energy of the nucleus. So what do you mean by the binding energy? That binding energy of the nucleus is the amount of energy needed to separate its protons and neutrons from the nucleus. So the amount of the energy is required to break. Basically, you have to break the nucleus. It measures of the how tightly the nucleons are bound together. So its formula is delta E, that the change in the nucleus. There are some initial energy, so they are bounded by each other. Then you are giving more extra energy to break the nucleus. So the formula is Z into mass of the proton plus N into mass of the number of protons into mass of the proton into number of neutrons into mass of the neutron. This is the sum minus the total mass of the nucleus into c square. Okay. There are so many another parts are there. The mass defect is the difference between the actual mass of the atom and the sum of the mass of this part. So mass defect is nothing but the actual mass of the atom, means that we can measure this atomic mass that in the AMU. So if I will say the mass of the atom is 1 gram, mass of the hydrogen is 1 gram, so it is not correct. There are some more, maybe very tiny level of mass is there, but yes, it is present. So mass of the hydrogen must be not exactly 1 gram for, but in round off we can assume that. But at the end of the day, we can assume that the mass of the hydrogen is not exactly 1 gram, but little bit of higher than the 1 gram. That must be 0.001. Mass of the carbon is 12.000.14 or something. But if we make the difference, that is the mass defect of the hydrogen. What will be the mass defect of the hydrogen? If anybody will ask, so mass of the hydrogen will be 1.00008 minus 1. So that is divided by the uh, atomic number. So this is known as the mass defect. And the packing fraction is the ratio of the volume of atoms in the crystal, the total volume of the crystal. And if E is greater than 0, for the binding energy is getting that, if is E is greater than 0, the nucleus is stable. Binding energy is greater than 0. If E is lesser than 0, the nucleus is unstable and will disintegrate itself. So if E, what is the if binding energy is greater than 0, the nucleus will be stable, and greater than, if the binding energy is less than 0, the nucleus is unstable and that will be disintegrate in itself. There are many more assumptions are there. That is the if reactant is greater than product, the reaction process will occur, and the if reactant is energy of the reactant is less than the energy of the product, the reaction will not occur. Here you can see the binding energy curve. So what is the significance of the binding energy curve? Any guess from that? Here you can see that the binding energy up to the atomic number, you can see the proton number, or you can see the number of nucleons. So you if you will see the up to 20, the proton number up to 20, that must be, you can assume that the calcium. So up to calcium, this is the binding energy is increasing rapidly. Just you can say that, you can see that the binding energy increases rapidly. Here some you can see that for the hydrogen it is here, for helium it is here, and for the helium, another isotope of the helium will be much higher. For lithium it will be little bit of lower, and up to calcium, here you can assume the calcium, it will be ranges between 8 to 9 mega electron volt, something 8.5 mega electron volt. So binding energy for the up to the lighter nucleus, that is 8 to 8.5, it ranges between 8 to 8.5 mega electron volt. Then for the heavier atoms, after beyond the calcium, if we study the periodic table after the calcium, so for the iron isotope, the binding energy will be maximum. That is near about to 8.7 mega electron volt per nucleon. Are you seeing that? Have you seen that? This is the mega electron volt. And if A ranges between, after that, that is from 57 to up to the last of the at the end of the periodic table. So it will become much lower. So the binding energy will be for uranium, that is the heavier isotopes, that uranium must be used for radioactive, uh, it has radioactive uses, and we can use the nuclear power reactors for to generate electricity. So for uranium isotopes, that it will become 7.6 mega electron volt. So this is the significance of the binding energy curve. So if I will say in short, that up to first 20 atoms, that the binding energy will rapidly increase. Then from 20 to 56, the binding energy will still going to increase, and that it will achieve the highest for the iron. And after that, it will significantly will decrease, and it will go on at the end of the periodic table, the last heavier atom. What we say for the uranium, you can see the binding energy of the uranium is 7.6 mega electron volt. Okay. So this is the basic of nuclear models. There are many more basic properties are there, but I am not discussing because our main motto is to discuss about the nuclear models. So there are lots of nuclear models: Fermi gas model, liquid drop model, shell model, collective model, Nielsen model, Bohr Motelson model, interacting boson model. So there are several nuclear models are there. So out of these seven, there are only three models, that is liquid drop model, shell model. This is more important because in now these days the shell model is most acceptable model right now here, and the collective model. These three are most important models for out of among all these nuclear models. So this is the nuclear models, liquid drop model. So here liquid drop model, we can assume the binding energy basically. So binding energy of the liquid drop model is the summation of the all the energy terms. You can see that, that is the VV. Here we can use the see the volume energy term, surface energy term, Coulomb energy term, asymmetric energy term, and pairing energy term. I will discuss this one by one, but you can see that the total binding energy is the summation of this all these terms. So volume energy term here we can assume that BV equal to plus AVA. So A is the, again, this is the atomic mass number. So total number, nucleon, total number of that means total number of protons and total number of neutrons are present. So what is the significance of the volume energy term? The number of neighbors of each nucleon is independent of the overall size of the nucleus. The other terms are corrections of the term. This is the correction term of the volume energy term. So this is the volume, which is used to determine the volume of the nucleus. That we can assume that the correction of the volume of the nucleus in the atom. Okay, so here is the surface energy term. Binding energy of the inner nucleons are higher than that is surface. So how we can see that the binding energy of inner nucleons? So for binding energy of the proton and neutron is greater than the binding energy of the surface of the nucleus. So the surface term is come as Bs equal to minus S a to the power 2/3. Here you can see that the volume energy, which is almost what can I say? It is very constant. And if you will see that the surface energy term, that it will constantly increasing with the increasing of the total number of nucleons. Here you can see that then the binding energy per nucleon, so that will constantly increasing for the surface energy terms. Again, the Coulombic energy term. The Coulomb energy term, what is the significance? The Coulomb energy term is the electrostatic repulsion between the proton in a nucleus. It is a term in the semi-empirical mass formula. What I am coming about the semi-empirical mass formula, but you can see that the Coulomb energy term is nothing but, you can see that the Coulomb's law. So do you know about the Coulomb's law in electrostatics? Okay. So this is all about the Coulomb energy term, and this is the asymmetric energy term. The asymmetric energy term that accounts the difference of number of protons and neutrons of the electrons. This is known as the Pauli energy. That means the asymmetric energy is basically measures the difference between number of protons and neutrons in a nucleus. So the asymmetry energy is known as the Ba equal to minus AA. This is the asymmetric term, and A minus 2z square by A. So this is the asymmetric term. And the pairing energy term, this is the extra bounding between the pairs of identical nucleons in the same state, Pauli state. So if we say that if there are several conditions of the pairing energy term, so the pairing energy term is determined as the delta is proportional to e to the power minus 3/4. It so the pairing energy constant is AP. This is here, and this is depends on the conditions of the protons and neutrons. If there are both the proton number and neutron number are even, suppose proton number and neutron number are 4 4, so the pairing energy term will be a to the power minus 3/4. If any one of them any one of them are odd and the other one is even, so the pairing energy term will be 0 for both cases. So you can say that the number of protons are odd but the number of neutrons are even, and vice versa. So the pairing energy term will be 0. So the condition of the pairing energy term will be non-zero. It must be both the number of protons and number of neutrons should be even or odd. If any one of them is odd or any one of them is even, so the pairing energy term will be 0. So, and here you can say the number of protons and number of neutrons are odd. So minus AP a to the power minus 3/4. So This is the negative pairing energy term we can say. So the effects of the pairing energy term is the fusion and magnetic moment of the nucleus. So I will discuss further later on that how to determine the magnetic moment of the nucleus. So effect of the higher angular momentum. So these are the main part of the pairing energy term. And if we at the end of the day, if we see that this all the semi-empirical mass formula, you can see that the binding energy, total binding energy will be EB equal to volume energy term minus of the surface energy minus Coulomb energy minus asymmetry energy plus minus that depends on the even odd condition where the number of the electrons will be number of the protons and neutron will be positive or even or odd, so that depends on the plus minus. So this is the semi empirical mass formula and the base.
Sir,
Yes.
sir, could you kindly also pay attention to the chat? There could be some questions in the chat.
Okay. So I am sharing, but there are if you want to ask, then you can stop me here. Okay. So Pauli state is nothing but that the this have you Agrima? Have you seen the Pauli exclusion principle? Agrima, have you read about the Pauli exclusion principle? Maybe in class 11, 12, you have already know about this. So this is the what do you mean by the Pauli state? So uh, the Pauli exclusion principle, that is basically known as the Pauli state. So see, there in quantum mechanics there are many quantum numbers are there: principal quantum number, azimuthal quantum number, magnetic quantum number, spin quantum number. There are many quantum numbers are there. For the Pauli state is knows that the states that two or more identical particles. What what do you mean by again the identical particles? There are many types of identical particles are there. So one of them is the fermion, another one is the boson. The fermions have the half integral spin, the bosons have the uh, full integral spin. So the Pauli exclusion principle states that the two or more identical particles with half integer spins cannot simultaneously occupy in the same quantum state within a system that obeys the laws of quantum mechanics. So this is known as the Pauli exclusion principle, and this is the state where the with half integer spins, that means the fermions cannot simultaneously occupy in the same quantum state. That means if you take any atom as an example, suppose for lithium. So for lithium, there are you will see the Aufbau principle, the Pauli Ohm's rule for filling up the electrons for shell. So there you must be heard about the SPDF states: A state, P state, D state, F states. There are. So for A states, not more than two electrons will occupy in the same level. For 1s, for 2s, for 3s, you can see that. For P states, not more than six electrons will occupy in the same level. So after that, it will go the further in the higher state. So this is the Pauli exclusion principle. So and this state is known as the Pauli state. Have you got it? Okay. So we should move further. So this is the liquid drop model, and there are the limitations are present in the liquid drop model. The basically liquid drop model has explained many nuclear phenomena, but there are certain limitations are there, that how to find out exactly where the nucleus lies in. And this does not give the concept of the magic numbers. That's I have already discussed that the SPDF states that in the A state there can we can in A state not more than two electrons will occupy in the same level. In P states not more than six electrons can occupy the same level. In D states not more than 10, F for not more than 15, and so on. So these are the basically the magic numbers. But SPDF, these states I am telling in now currently in the atomic way, but in nuclear physics and quantum mechanics level, there are many substrates are also there. So by adding all these substrates, we get the magic numbers of the nucleus. So the liquid model doesn't unfold the concept of magical numbers. Magic numbers of proton neutrons fails to explain detailed quantum mechanical effects of individual nucleus, what I have discussed earlier, and the struggles accurately to describe behavior of light nuclear excited nucleus. Yes, so there are many light nucleus, there are excited nucleus, but from nuclear model we cannot get that from this the binding energy concept that the which nuclear is heavier, which nuclear is lighter. It does not capture the shell structure of the nucleus. So you have must heard about the in your JE preparation or other. Don't know that others are maybe from those who are from MSc background from your JAM preparation. So you must be heard about the shell structure of the nucleus, the KLMN, the shell, KLMN shell, and there are subshells of SPDF shells. So it can't describe about this the shell structure of the nucleus. That's why shell model is introduced. So what is the shell model? It describes the arrangement. First you have to we can easily describe the magic numbers from the concept of shell model. The arrangement of electrons in an atom that is filled in a shell always leads to greater stability. There are certain magic numbers of the nucleus 2, 8, 20, 20, 28, 50, 82, 126 that are more tightly bound than the subsequent higher number, which is the original condition of the shell model. So I will describe that what is magic numbers. Let us assume the basic of the shell model. So the shell model, you have to know about this the what is basically the uh, shell structure is defined. So do you know about the shell structure, that what is K shell, what is L shell, what is M shell, what is N shell, and so on. So do you know about anyone? K shell, how many maximum number of electrons can occupy in the K shell? What is the maximum number of electrons can occupy in the L shell and M shell, N shell? Do you know?
Yes, sir.
Okay. So so this is the basic that the how many electrons will occupy there. So that that will be one second. That will be 2n square. That will be 2n square. This is known as the shell model. So for if we put a k equal to 1, so for k shell, so maximum 2 into 1 square equal to 2. That will be the 2 must be for the K shell, and for L shell that will be 2 into 2 square. For L is equal to 2 square. So for 2 into 4 8. For L shell there are maximum 8 number of electrons can occupy. Same for M shell for 3, M equal to 3. So this is the known as the principal quantum numbers. So we are describing. So this is the shell model graph. So not sorry, no, it is not the shell model graph. This is the shell model concept, the shell structure that you can see. So before that, I am So you can see that no, I will be text. Before the shell model, the electrons and these are move in a very harmonic way, that they move in a very harmonic way. So the there are one potential is occur which is known as the Wood section potential. So this is basically describes about the shell model and shell structure. So this is basically known as the V equal to VR VR minus of F into L dot H is. You can take the expectation value of L expectation value of this is the modified Usatson potential, because only if for take the in the binding energy liquid draw model there, this is basically known as the V equal to VR. But in shell model there are one interaction occurs which corrects the liquid draw model. That's why shell model is introduced. This is known as the spin orbit interaction. This part is Fr into L dot H. This is basically arise due to this is known as spin orbit interaction. That spin orbit interaction we have discussed in the this we have discussed in the atomic energy, and you can take any standard of standard books, so you will get this idea about elementary idea about the spin orbit interaction. So if we take from the vector atom model, so that is J equal to L plus S, where J is known as the total angular momentum and L is the uh, total orbital angular momentum and S is known as the spin angular momentum. So L is the orbital angular momentum. There we all know that for if you take the S equal to for if for A state L will be 0, for A state L will be 0, for P state L will be 1, for for D state L will be 2, and so on. So this is the spin orbit interaction. If again if we take the square of the both sides, so if you will get that if we take the square of the square of the this vector atom model J equal to the L plus S, then we will get that J square equal to L square plus S square. So if we square of them, then will we go that so S square plus A square plus 2LS. So if we get if we this is the expectation value of the spin orbit interaction. So if we take the expectation value, so we all know the expectation value of J square will be J into J plus 1 into H cut square. Same for L state will be L into L plus 1 into H cut square. For S will be S into S plus 1 into H cut square. And from that we will get that the final if we get that the expectation value of L square, that would be equal to j into j plus 1 into h square plus if we get that my sorry, that will be, if we take this the other side, so that will be the L into L plus 1 into h cut square minus of s into s plus 1 into h cut square divided by 2. The whole thing will be divided because there is a 2 term is present. So this is the expectation value of j. But if you will see that how this 2 is coming, this 2, this 8, this 20, 28, 50, that how this 2 is coming. So j into j plus 1 into h cut square. So if we take that j equal to s, if we put this the value j equal to s, so if we take this the 1 s2, this is the from the spectral configuration of an atom. This is basically 2s plus 1 s half. This is the spectral configuration where 2s plus 1, this is the number of spin states. 2s plus 1 equal to 1. So this, here I can write this. So there I can write is 2s plus 1 equal to 1. Here this 1 is, you can see that that 1, this is the total number of spin states are there. So the how many spin states are there? There will be no spin states, because if from the calculation we can get s equal to 0, and s is basically denotes the orbital angular momentum. So for that I have already said that for the a state L will be 0. For a state L will be 0, and for the j, this is the half is basically denotes that the total angular momentum. So from the total angular momentum, so j will be j equal to half. Okay. Similarly, we can find this, but we will discuss later. So from this, if we put this value here, if we put this value here, we will get that the expectation value of L and S will be 0. So expectation value of L and S will be 0. So there from this the analogy, or from these assumptions, we can conclude that there is no substrates will there for the A state, one state. There will be no substrates will be there. So this is all about for the, and from this the two number is coming from the selection rules, from the selection rule of the j, because the selection rule of the atom will be 2j plus 1, or that means 2j plus 1. If we put j equal to half, then you will get the half, 2 into half, 1, 1 plus 1 2. So maximum 2 atoms will occupy this state. This is known basically the this is so for the one state there will be two atoms will be there. If we go the 1p state, so it will be split into the two levels. How? Let's check. For p state, that is L equal to 1. So p state for the L equal to 1, and for s state, so for p state L equal to 1, and s will be same here. For 1p, there 2s plus 1 equal to 1, so s equal to 0. So j will be, so the j will be here for either half. J will be the standard formula of the j will be L plus half. This is basically known as the stretch case, and j will be L minus half. This is known as the jackknife case. This is basically known as the stretch case. Stretch case and this is basically known as the jackknife case. So for if we take j equal to half, 1 plus half, so that will be the 3 by 2 j. And if we will take j equal to 1 minus half, so the p will be half. So from this condition, that two states have come, and from the number of atoms that if from the selection rule of the 2j plus 1, if we put 2 j equal to 3 by 2 here, so you can see maximum 4 electrons will occupy this state, and for half state maximum 2 electrons will occupy this state. So this is basically known as the 2 plus 4 equal to 6 and plus 2 equal to 8. So the magic number of the 1s state will be 2 and the magic number of the 1p state will be 8. So similarly we can go up to the higher level. So this is basically known as the shell model. So basically from this shell model we can find out the parity of the some nucleus. So the parity will be positive or negative and the total angular momentum of the nucleus. So if you will see that, so the from the Hund's rule you can see, from the above principle we can see the 1s2 2s2 2p6 3s2 3p6 and so on. But from the shell model you can see that the 1s half, then 1s half, how many electrons that will occupy? Maximum 2. So 1s half 2, 1p 3 by 2 4, 1p half 2, 1d 5 by 2 6, 2s half 2, and it will go the so on up to higher atom levels. So this is all about the basic principle of the station model. I have given the basic outline of the vector atom model, and from the vector atom model we have find out this the uh, basic configuration, that how to this the table has been introduced. So this is all from this side, and another one I am discussing here. So the ground state parity condition. So we have got the shell structure and how to represent a nucleus in a shell model manner, that we have discussed. That if we say see that some, I will discuss some examples later on after explaining this stuffs. So for even proton, even neutron, so J will be 0. If the proton number will be even and the neutron number will be odd, so the proton number will be, so Jp equal to 0. For even we will not consider the total angular momentum, and the Jn will be Z. If for odd Z, odd and even N, so the proton number will be considered by the total angular momentum and Jn will be 0. And odd Z and odd N decided by the not the M rule. So there is there the Jp minus Lp plus Jn minus Ln. And the parity, how will we describe? So the proton number will be there will be the J to the power pi equal to minus 1 to the power Lp. Lp is the orbital, that where will be the S, P, D, F or so on. So for odd proton, so we will describe about the parity. So for Lp, suppose I am finding out some atom and it has come that 1d 5 by 2. So the 1d, for the 1d 5 by 2 states, so d will be 2, and so we will put the minus 1 square, so plus 1. So plus 1, so the parity will be even. If it come the F state, F equal to 3, so minus 1 to the power 3, that will be minus 1. So the parity will be odd. And for odd neutron, the same procedure will follow. And if we, for the odd nuclei, we will add the both of the nucleus, because there are many more isotopes there. We will get the odd number of nuclei, odd number of protons, odd number of neutrons. So we will just add their parity. Okay, we will find out the shell structure, we will find the shell configuration, and then we will get the L values, and just we will sum up to the power of the minus 1, and we will get the parity of the nucleus. So, and the last thing that I will describe about the G factor of a nucleon for odd proton, it will be 0.001. G1 equal to G, that is the odd proton, G will be the 1, and for the orbital G factor, this is known as the orbital G factor. In the atomic physics, we will get many more terms, that is Landé G factor, orbital G factor, spin G factor. Landé G factor is all about the describes the total angular momentum, and for the orbital G factor only the G term will be present. So the G value will be 1 and GS will be 5.58, and this is basically the known as mu equal to I. This is the nuclear spin. Just we can know that we have described the total angular momentum expectation value will be j equal to j into j plus 1 into h cut square. For I, that will be the I into I plus 1 into h cut square. This is the nuclear spin I, and this is the nuclear magnetic moment mu equal to I plus 2.29. For I equal to I plus sorry, for L equal to I plus half, and mu equal to I minus 2.29 into I by I plus 1 for I equal to L minus half. And for odd neutron, GL will be 0 and GS will be minus 3.82 and mu will be minus 1.91 for I equal to for L equal to I plus half and minus 1.91 I by I plus 1. So this is the G factor of a nucleon. So let's discuss one problem. Here you can see the ground angular momentum of the 17A2 nucleus. This is the isotope of an oxygen, that we can see that we have to first measure the number of protons and number of neutrons. So number of protons will be 8, as we have discussed earlier, that you can see that I have discussed, if we get the even z odd n, here you can get even z, proton number is 8, neutron number is 9. So we will get the even z, and but neutron number is 9, so odd n. So for what is the condition for the odd n, even z and odd n, jp equal to 0. So the angular momentum of the, what we will find out, angular momentum will be 0 for the proton, and for the neutron we have to find out the angular momentum. Why it is 0? If you will see that all that 2 4 6 8, the all states are occupied, so each state will repel out each other. Each state, because it is one is the for it, suppose let us assume there are two electrons. This electron is positive, this electron is the spin of this electron will be positive plus half, and the another one will be minus half. That is the what we have discussed na. This is will be the plus half, this will be minus half, so each of them will be opposite each other. Same, there will be four electrons, each of them will be opposite each other, and there will be the two electrons, so each of them will be opposite each other for the different spin states. One spin state will be plus half and another spin state will be minus half, so that will be become 0. So each of them will repel each other, so the total angular momentum will be 0. So that's why this is the physical concept, and for mathematical concept that I have also discussed. So we have to take the only neutron part, only because there are the proton number is 0. So what will be, there are total 9 neutrons. So if we go there, so there are two, one is 2, 1 p 3 by 4, 1 p half equal to 2, and 1 d 5 by 2 equal to 6. Here, so two electrons will occupy in this state, 4 will be occupy in the p 3 by 2 state, 2 will occupy in this state, and the remaining one will go. So you can see that there maximum you can occupy 6, but here is only 1. So there will be some angular momentum value. So this is the physically I am describing, but and mathematically we will get 1 is 2, 1 p 3 by 4, 4, 1 p half 2, and 1 d 5 by 2, that will be 1. So that will be the shell configuration. I don't have the pentap with me right now, but uh, if I will for the if it has happened in the offline session, that I will be described by writing in this on the whiteboard. So don't worry. So there will be the, so 1 is half. So the final answer will be 1 is half 2, 1 p 3 by 4, 4, 1 p half 2, and 1 d 5 by 2, 1. So the angular momentum of the J will be the answer D, because the final electron will occupy the J equal to 5 by 2 state. So this is the correct answer. J 5 by 2 states. So this is the total angular momentum of the ground state of the 1708 nucleus. And one thing is more, that if anybody will anyone will ask that the what will be the parity of this the ground state of the 1708 nucleus. So parity will be here, that I have already described. For odd neutron, -1 to the power ln. So ln here, what you can see, d equal to, here is 1d 5 by 2. So d equal to 2. If we put here ln equal to 2, that we will get the -1 to the power -1 square. So we will get the parity will be positive, that is +1. So the final answer will be the, if it will ask the ground state, here they have only asked the total angular momentum, but if they will ask the ground state parity of the J of the ground state of 1708 nucleus, is that will be 5 by 2 positive. That will be the answer. That will be the right answer. If it will become the, it will become P, so that the parity will be negative. So this is the all that I have talked about. This is the shell model. And here you can see that another question that I will be share in the pack reading circle group, and interested one should follow, interested one should solve, and they will, if they have any doubts or queries, they can reach out to me for any time. So that's all from my side. If any question or queries are there, you can ask.
So maybe you can also look at the chat.
Okay. Okay, so what is the physical significance of parity? The parity basically describes that the angular momentum will be positive or negative. Basically the state. This is the quantum state. Basically, we are seeing that this is all the quantum state. Whether the quantum state will be positive or negative, because there are two types of. We can describe from the two types, because all these what we are describing here, these are the identical particles, where the electrons will be, the particles will be, you can say fermions or bosons, they are identical basically in nature. So because if you will see that these particles are identical, so how we can distinguish them? So parity does that job, that yes, this atom is this particular particle has negative parity, this particular particle has positive parity. If you will see that in this question, the ground state parity, here you have asked that 1708 nucleus. You can see that. If we'll say, here we have asked the ground state. If I will ask at the first excited state, so the parity will be changed, because the one electron will go the upper, will be excited and go on to the higher level, higher energy level. So the parity will be changed. So the parity basically defines the quantum state. So that we will get from the uh, identical particle concept, because there are many more. You have to want to see that, you can ask me again for further, because there are lots. If you will ask that the concept of the parity, so it is very very huge, where within 10 minutes or 15 minutes I can't explain properly, but I can give that assurance that the parity basically basically describes the quantum states. So that's why the quantum states of the particle, whether it will be the positive, the whether the particle will be positive or negative. So that's why. Another. Okay. So any questions from other side? Okay. So okay, I am sharing my screen here. So I'm stopping here. So
Uh, Does anyone have any questions? Or we'll end the meeting.
Uh, and I want to know one more thing, that how was that the reading circle? Because for the first time I have taken that, that I have not get so much proper time to prepare myself, because these are all the gate have came in the gate syllabus. So I didn't get so much time. So if you have any queries, or if for the next reading circle, if you want me to again to do so, so what rectifications are required, so let me know. So that will be beneficial for me to prepare and brush out
If
myself more.
anyone can give feedback in the reading circle group,